Section 20.3, the Equipartition of Energy. In this session, we will explore the fundamental contributions to molecular energy and the theorem of equipartition of energy. We will specifically examine how this applies to the molar-specific heat of diatomic gases and the complex role that vibration plays in larger molecules. Finally, we will discuss how temperature dependence and the quantization of energy levels explain why classical physics sometimes fails to predict the behavior of these gases at different temperatures. To understand the energy of a gas, we must look beyond simple movement. While temperature is a direct measure of the average translational kinetic energy associated with a molecule's center of mass, internal energy is more comprehensive. It includes internal motions, such as the rotation of the molecule around its center of mass and the vibration of atoms within the molecule itself. These various forms of motion are not isolated. They are coupled to translational motion through constant molecular collisions, allowing energy to be transferred between different modes. The equipartition theorem is a cornerstone of statistical mechanics. It states that for a large number of particles, the available energy is shared equally among every independent degree of freedom. At thermal equilibrium, each of these degrees of freedom contributes an amount of energy per molecule equal to 1/2 times the Boltzmann constant times the absolute temperature. This classical model is essential for explaining why the molar-specific heats at constant volume and constant pressure vary between different types of complex gases. Let us look at a diatomic molecule, often modeled as two atoms connected like a dumbbell. This structure has several degrees of freedom. First, there are 3 degrees of freedom for translation along the x, y, and z axes. Next, there are 2 degrees of freedom for rotation. While it can rotate around the x and z axes, we neglect rotation about the y-axis, which is the axis connecting the two atoms. This is because the moment of inertia around that specific axis is so small that its rotational energy is negligible. Excluding vibration, this gives us a total of 5 degrees of freedom. Using the equipartition theorem, we can calculate the internal energy for a gas with n molecules and 5 degrees of freedom. The internal energy equals 3n times 1/2 the Boltzmann constant times temperature for translation, plus 2n times 1/2 the Boltzmann constant times temperature for rotation. This simplifies to 5/2 nRT, where n is the number of moles and r is the gas constant. From this, we find the molar-specific heat at constant volume is 5/2 R, or approximately 20.8 joules per mole Kelvin. The ratio of specific heats, gamma, is 7/5, which equals 1.40. When we include vibration, we model the atoms as being joined by an imaginary spring. This adds 2 additional degrees of freedom, 1 for the kinetic energy of the vibration and 1 for the potential energy of the spring. With translation, rotation, and vibration all active, the theorem predicts an internal energy of 7/2 nARET. This leads to a predicted molar-specific heat at constant volume of 7/2 R, or 29.1 joules per mole Kelvin. However, there is a problem. This full classical prediction does not match experimental data for gases like hydrogen and nitrogen at room temperature. This graph shows the molar-specific heat at constant volume for hydrogen across a wide range of temperatures. On the left, at very low temperatures below 100 Kelvin, the gas behaves like a monatomic gas, with a specific heat of 3/2 R because only translation is active. As the temperature rises toward room temperature, the curve plateaus at 5/2 R, showing that rotation has become active while vibration remains dormant. At very high temperatures, above 2000 Kelvin, the specific heat finally reaches 7/2 R, indicating that all motions, including vibration, are contributing to the energy. The failure of classical physics to explain why some degrees of freedom seem to freeze out at lower temperatures is resolved by quantum physics. Energy levels in a molecule are quantized, meaning only specific, discrete energy values are allowed. For a particular motion to contribute to the specific heat, the environment must provide enough energy to cause transitions from the ground state to an excited state. As shown in the diagram, vibrational energy states are much further apart than rotational states, requiring significantly more energy to become active. Quantization explains the temperature dependence we see. At low temperatures, the energy from molecular collisions is insufficient to push molecules out of their ground state, so rotation and vibration are frozen out. As temperature increases, the average collision energy reaches a threshold that can excite rotation. For hydrogen, this begins around 500 Kelvin. A much higher temperature, roughly 5,000 Kelvin for hydrogen, is needed to reach the threshold for vibration. Polyatomic molecules with even more atoms have even more degrees of freedom and higher predicted specific heats. In summary, the equipartition theorem predicts an additional 1/2 R for every active degree of freedom in the molar specific heat. Diatomic molecules possesses 3 translational, 2 rotational, and 2 vibrational degrees of freedom. While classical physics incorrectly predicts these should always be constant, experimental evidence shows they depend on temperature. Quantum mechanics clears this up by showing that degrees of freedom only become active when the thermal energy, represented by the Boltzmann constant times temperature, is large enough to excite them. To wrap up, consider a diatomic gas with a measured specific heat of 5/2 R. Based on what we discussed, which motions are active and which are frozen out? Also, think about why the rotation around the molecular axis connecting the two atoms is considered to have negligible energy. Reviewing these concepts will help solidify your understanding of how energy is distributed at the molecular level.